Hello everyone, welcome to my calculus lecture. In this lecture, we study the first and the second derivative test. Okay, so we begin with the following theorem, which is called increasing decreasing test. So here's what the theorem says. If f prime of x is positive on an open interval, f is increasing on that interval. If f prime of x is negative on an open interval, f is decreasing on that interval. Okay, so let me use a simple example to understand the theorem. Yeah, what I meant to draw is the graph of y equals x squared. That's it. A simple example, right? And as you can see on the left side of x equals 0, so for all, the negative x, right, the graph is decreasing, right? As x increases on this interval, so from negative infinity to 0, right, the graph is decreasing as x increases. Okay, on the other hand, on the interval from 0 to infinity, right, the graph is increasing as x increases. Okay, so we want to see how, this is related to, so increasing, decreasing property of this function here, y equals x squared, how that is related to, especially the sign of f prime of x, right? So, try to draw like a tangent line. Yeah, that doesn't work out very well. Okay. Actually, I'm gonna draw just one. All right, I don't want to mess up more. But if you draw actually a tangent line and any like the x value, right, on the interval from negative infinity to 0, you will see that. Okay, the slope of tangent line is what? Negative. Okay, slope of tangent line is negative. So we see the relationship between the sine of f prime of x and the graph of a function being decreasing, right? Okay, and likewise, on the right side, if you pick any x, right, on the interval from 0 to infinity, and consider tangent line at that point. You see that like the tangent line the slope of tangent line is always positive. Okay, so the sign of it. So now we see that the sign of f prime of x, right, characterizes, right, actually it determines whether, the function graph of the given function is decreasing or increasing on a, on an open interval. Okay, so the theorem, now we see that like why the theorem makes sense. Okay, so here's an example. Find where f of x given by 3x to the power 4 minus 4x cubed minus 12x squared plus 5 is increasing and where it is decreasing. Okay, so we're going to use this theorem to determine that. Okay, so the function we have here is f of x equals 3x to the power 4 minus 4x cubed minus 12x squared plus 5. All right, so we want to determine again, like, the intervals, right? The intervals on which f of x is increasing or decreasing. All right, right. So here's the first step. First step is if you remember, right, a while back in one of my earlier lectures, I was mentioning when I was defining a critical point, I mentioned why they are actually called critical points. The critical points are called critical points because at those points, the state of function, the state of the given function changes from increasing to decreasing or decreasing to increasing. All right. For that reason, you know, the what we first have to do is to find the critical points first, because that's where the state of function changes from increasing to decreasing or decreasing to increasing again. Okay, so that's first step. So first step, step one is we need to find critical point. All right. So what do? We take the derivative, right? F prime of x. So that's going to be 12x cubed minus 12x squared minus 24x. No big deal, right? Now, all three of them, right? Notice that all three terms have what? 12x in common, right? So let's factor it out. 12x is factored out. So what's remainder is, in this case, x squared. Here, that's going to be x minus 2, right? And this is the one inside the parentheses is factored to x minus 2 x plus 1. Okay, so if you set this equal to 0 to find the critical point, right? We have three critical points, right? So three critical points. Okay, x equals in order, right? Negative 1, 0, 2. So we have three critical points. So what's the next step? So next step is, in order to use the theorem effectively, I actually prefer to use a table. A table where you can put all the information available together in one place, so you can see actually the whole picture easily. All right, so we are going to make a table. Okay, right. Since we have three critical points, I'm going to have the what is that? The Yeah, I'm going to need a column, so you are going to see that. So I use this. I'm gonna need three rows and eight columns. Let's see. I think this will give me enough space. Okay, I've got eight columns, I believe. 1, 2, 3, 4, 5, 6, 7, 8. Okay, right. Okay, so we are good to go. So here, first column is for x f of x, f prime of x, and last one f of x. Okay, and here three small columns you see, right? Those are for the critical points. So this is negative 1, 0, 2, right? At critical points, we know, of course, f prime of x is 0, right? 0, 0, 0. Okay. Now these three critical points divide, the entire real line into four parts. Okay, right. First, the when x is less than negative 1, right? Less than negative 1. In terms of interval, that's what interval, where the open interval, negative infinity to negative 1, right? And between these two, so x greater than negative 1 less than 0. And here x greater than 0 less than 2. And the last interval is going to be x greater than 2. So next step, we are going to fill, what is that? Second row, right? So second row is for the sign of f prime of x, okay? So we want to see what happens to the sign of f prime of x on each open interval, okay? But how do we do that? Well, for that, we are going to use something called the test point method, okay? Where should I write? Yeah, I'm going to use something called the test point method. I believe that you have heard of the test point method, sometime in the past, okay? Especially when you were studying algebra, right? More specifically, when you were studying like what? Solving, the polynomial inequalities, right? Solving polynomial inequalities. Uh, you used this method, the test point method. That's one of the common methods to solve polynomial inequalities. All right. I don't know if your teacher told you why it works, but that's due to the continuity of a function. If I give you a heads up. Okay, so here's how the method works. I mean, there's no humanly possible way you can examine all the, you can examine, what is it, the sign of f prime of x for all the, the x values less than -1, because what, there are infinitely many, points, right? But don't worry, we don't have to. All you have to do is just pick one point, one test point, and then check the sign of f prime of x. Okay? Right. So in this case, so our interval is from -1 to negative infinity to -1, right? X less than -1. So normally, like I would pick like the most simple number within that the interval, right? That's easy for you to calculate, right? So I would actually choose, in my case, I mean, you can choose any number as a matter of fact, but I'm going to choose the test point x equals -2. Okay, so let's check this sign. This is our f prime of x, right? So for x -2, this is going to be negative, this is going to be negative, this is going to be also a negative number. We don't need a value, we just need a sign. Okay, so the multiplication of three negative numbers, is an overall negative number, right? So the sign is negative, so we put negative sign there. Again, I used only like the one test point, and how does this guarantee that f prime of x is going to be negative for all like the values of x that are less than -1? That's because look at this f prime of x. F prime of x is also a polynomial, so it is a continuous function, right? It is a continuous function. So the continuity of this f prime of x guarantees that you know, it is the sign of f prime of x is going to be negative for all x values less than -1. The reason for that, if you don't see this still, the reason for that is this. In order to change it, right? So let's say that like oh, there is some like x value which is less than -1. For that value, like f prime of x is positive. Is that even possible? No, because because of continuity, the from for f prime of x to change from negative to positive, what happens? F prime of x, the graph has to pass the x-axis. In other words, at some point within that interval, right, from negative infinity to -1, f prime of x has to be 0. Is it true? No. There are only 3 points, -0, -1, 0, 2. Those are the only points where f prime of x equals 0. So because of that, it never happens. Okay, so that's why we know that due to the continuity of f prime of x, I mean, we just use the one test point, but that guarantees that the sign of f prime of x, right, is negative for all the values in that interval for all the values of x that are less than -1. All right, so moving on to next interval, uh, x greater than -1, less than 0. So pick one, the test point. In this case, I will choose x equals easy number. Okay, so for me, that's going to be -1/2. So x equals -1/2 case, this is going to be negative, this is going to be negative, but this guy is positive, right? 1/2. So that's going to be altogether positive. And here I'm going to use x equals 1. So that'll make positive, negative, positive. So that's going to be negative. And here I will choose x equals 3, 4, my test point. So that's going to be positive, positive, positive. So it'll be positive. Now, the third row is where the theorem we just learned, right? So increasing, decreasing test comes in. All right. So for f, because when x is less than -1, f prime of x is negative. So that means the graph is decreasing. So I'm going to use this notation, decreasing. And for the interval from -1 to 0, f prime is positive. So the graph is increasing. Okay. And here, for the same reason, decreasing and increasing. Okay, so we found out. Now all you have to do is just write this down. Okay, so the answer here is f of x is decreasing on the interval, right? -infinity to -1 or 0 to 2, right? So or we use this notation, right? Cup union the open interval 0, 2. So that's where the graph of f of x is decreasing and f of x is increasing. On the interval -1 to 0, open union here, right? 2 to infinity. Okay, so that's going to be the answer, right? Okay, so here comes the first derivative test. So what does it say? Suppose that C is a critical point of a differentiable function f of x, right? If the sign of f prime of x changes from positive to negative as C, f of C is a local maximum. If the sign of f prime of x changes from negative to positive as C, f of C is a local minimum. Basically, this is what I talked about, right? In one of my previous, the lectures. But I'll talk about more. Let me finish this first, okay? And then the last statement says, if the sign of f prime of x does not change as C, f of x has neither a local maximum nor a local minimum as C. All right? So let's take a look at the first statement. If the sign of f prime of x changes from positive to negative as C, f of c is a local maximum. Why is that? You know, the sign of f prime of x changes from positive to negative means that f of x, right, according to our previous theorem, which is called what? Increasing, decreasing test, right? The graph of f is increasing, it changes, right, from increasing to decreasing, increasing to decreasing. So locally speaking, locally we have this kind of shape. I'm just drawing like local point, okay? The local portion of the entire graph. So that's where like the critical point C is, right? So from increasing to decreasing. So at that point, we have what? Local maximum, okay? Local maximum, okay? So f of c, as a matter of fact, in this case, f of c is going to be our local maximum. Likewise, if the sign of f prime of sign of f prime of x changes from negative to positive, that means f of x is the changing from decreasing to increasing, right? Decreasing to increasing. So locally we have this kind of shape. So this is where the critical point C is, right? So locally, so decreasing to increasing at C, so that means the our f of c here is going to be a local minimum. Okay, this is going to be a local minimum. In this case, that's local maximum. If the sign does not change, then f of x has neither a local maximum nor a local minimum. Actually, I showed you an example, right, in one of my, the earlier lectures. If you remember, that was what? Y equals x cubed, right? So in that case, x equals 0 is a critical point. However, the sign of f prime of x does not change at x equals 0, right? And it turns out that, in fact, the f of 0, which is 0, is neither a local maximum nor a local minimum. We talked about that before, okay? So that kind of points are called, the saddle point, like as in horse saddle, okay? Right? I mentioned that too. Okay, so here's an example. Find and identify all local maximum and local minimum values of the same function that we talked about earlier, right? And actually we have the answer. So let me go back to my notepad. In fact, I'm gonna go back to my earlier, uh, the table. So here, the graph changes from decreasing to increasing, or f prime of x, the sign changes from negative to positive. So here, actually, that is also benefit of, the using these arrow signs. So this resembles, right? This clearly shows you decreasing, increasing, right? So, this part here, uh, what is that? It's going to be you can easily see that f of negative 1 is going to be a local minimum. Okay, so that's f of c, f of negative 1. That's yeah, I think I'm going to use actually red color, right? So that's a local minimum. Okay, and right? That's f of 0, right? And this is f of 2. F of 0 is going to be increasing, decreasing, right? So that's going to be local maximum. And f of 2, decreasing, increasing, so that's going to be local minimum again. So there is only one local maximum, local maximum. This is a local minimum again. Okay, cool. So I'm out of space, so moving to a new page. So for the example, by the first derivative test. So the really like good thing about using the table is that not only it provides like what all the information you need like in one place, right? So you can see actually the big picture easily, but also like you get all the answers too, right? Where the graph is increasing or decreasing, local maximum and local minimum. Just from the table, you get everything, right? So by the the first derivative test, right? We see that uh, f of 0, which equals 5, right? 5. So that's going to be a local maximum. And f of negative 1, f of negative 1 uh, equals 0, and f of 2, okay, f of 2, negative 27, those are local minimum values, okay, local minima. Good. Okay, I think this is good point where that we can stop, and I'll continue the second derivative test. Separate the following lecture. Okay.